Yeah. Thank you very much to the organizers for inviting me to give a talk today, or for letting me give a talk today. Thank you very much. My name is Kevin Grosvenor, and I am a postdoc at the Lawrence Institute in Leiden. However, the talk that I'll be giving today was work that I did while I was a postdoc at the Max Planck Institute in Dresden. And the question that we were interested in was, how does information flow through a neural network? And we have, I will venture to say, some sort of partial answers to this. I think this is still a very much an open question. Machine learning has, sort of just grown exponentially in the past few years. And I think it's fair to say that our theoretical understanding of exactly how they work, or how this process works, is lagging behind the enormous, impressive achievements that people have done with machine learning. And that's why we were sort of interested in this question. And I should say quickly, I won't go through all of these, but just in case, I don't necessarily mean to say that anyone here thinks machine learning isn't important, but in case you might think that it has nothing to do with your everyday life, I mean, here's just a smattering, a very small collection of ways in which machine learning affects our everyday life, at least, very obvious things. Obviously, if you use any form of social networking or smart assistants like Siri and Cortana, whether or not you know it, that you're even using these things. Some of us don't know that it's on in the background. Then machine learning is at least in the background in your everyday life. And there's so many other examples. I just want to mention this one just because it's important for my workflow. I don't know if anyone else here uses it. The service called iArchive. I use it to sift through the new papers that appear on arXiv every day. As we all know, probably, there's an enormous amount of research that just, we're just bombarded with every single day. And the way iArchive works is, I think initially it constructs a vector of preferences of themes or topics for you. Initially, I think it does that based off of your own research. And then it will project the new papers that appear every day on the arXiv onto that vector. And the ones which have a stronger projection will be, well, it will list the new papers according to their strength of the projection onto that vector. But that vector also is dynamically updated based off of your clicks, the papers that you choose to read. Okay, so in principle, the longer you use this service, the better, in principle, it should be, the better it is at actually telling you which things you're interested in. Machine learning has also, of course, reached this zeitgeist of common use since it has so many uses. And appears in news, of course, that generally will mean some amount of sensationalism. I just want to warn us against this sort of thing. So here's an article in the Quanta magazine, which came out, I think, in maybe 2016. There was some time ago when the first kind of, let's say, concrete suggestion of this relationship between renormalization in physics and deep neural networks. And it implied, if not explicitly, at least implicitly, that that's how it works. Here's a rather vitriolic comment in the rather interesting comment section of this article, which gives you a sense that it's really quite a bit more complicated than this. Yeah. So I think that the question is still very much open, though I do like this analogy between renormalization and deep neural networks. I don't think this suffices to explain everything. Certainly not all aspects of the learning part of machine learning. Nevertheless, we should discuss, fantastic. I forgot to set the timer, so I guess, thank you. Nevertheless, I think it's worthwhile to discuss, intuitively, what is the idea? It's a rather intuitive idea, really, especially if you're used to, working with renormalization. I mean, what is the sort of quintessential use case of machine learning? One of them is certainly in image recognition. I give you a collection of images that are presumably within some subset of categories. These categories have to be predetermined. You can't ask a machine to just know absolutely any possible object. Okay? Here it's some subset of US presidents in this example. Okay, and what does it do? Well, it breaks down the image into just a string of pixel values. And then there's one neuron for every single pixel. The pixel value will tell you how black it is, how gray it is, how white it is, and so on. And then it pushes that through a series of neurons, a series of layers of neurons. And these connections here, which connect the neurons, it's just some rule, some Markovian rule to tell you how you go from neuron in this layer to neuron whatever in this layer, and so on and so forth. Importantly, in this particular simple feed-forward, what's called a multi-layer perceptron, only layer, let's say, input layer is connected to first layer is connected to second layer. There aren't any sort of connections that go across layers. Okay, of course, you can also consider that, but this is the simplest architecture. And in principle, what is supposed to happen as you go from layer to layer to layer is that you start from just the raw data, which is just pixel values. And in principle, these layers are supposed to extract increasingly abstract information about that data. So in the case of an image, it might sort of extract the line edges in that image, and then collections of line images, and then somehow build from that more abstract features. In facial recognition, that might be, a nose or an eye or a mouth or something like this, until you finally get to the final output layer, which is some set of categories. Okay. Implicitly, of course, the information is there to begin with. It's there in the pixels. You're not getting something out of nothing or more than you put in. Right? In fact, you must be losing information. Right? I mean, there might be a billion images, all of the same object. They're all different. Obviously, in this image, this cat is lying down. In this image, this cat is jumping up. Right? They're very different images, but at the end of the day, the output is just cat. So you're obviously losing information here. And that's rather sort of analogous, if you think about it, to the way you kind of lose information in the process of renormalization in physics. So here's just a sort of super duper cartoon of the idea of renormalization. The idea of renormalization is that, well, look, let's say I do particle physics. I don't know the fundamental theory of the universe. I don't know what happens at extremely, extremely high energies. And extremely, extremely high energies tends to coincide with extremely, extremely short distances. So it's convenient to think of you sort of, well, I don't know what's happening at these, let's say, imagine these are sort of quantum fluctuations. I don't really quite know what's going on here, but if all I'm concerned about are sort of physics at long distance scales, then I can wash out all of these sort of small fluctuations and you just end up with this. Essentially, renormalization in this sense, or in this picture, is just a low pass filter. Yeah. And that's just because, well, look, I don't know. I'm not going to get into the debate of frequentist versus Bayesian, but this is more like a Bayesian language, right? Like where I say, well, look, I'm simply ignorant of what happens at extremely high energies. So I'm going to do my best and give you predictions for low energy degrees of freedom, given the fact that I'm ignorant of the high energy degrees of freedom. Okay. So the process of losing information in going from high energy to low energy, well, it's very natural to make a connection between these two pictures. By the way, just for future, in the way we're going to construct these neural networks, these lines here, which are the rules which tell you how to go from layer to layer, they'll be randomly distributed. Okay, so you pick some number. There's some rule, which is some like linear, let's say linear transformation from left to right. And let's say we'll just pick some random matrix or something like that, which takes you from here to here. Okay. And then you could, in principle, choose whatever distribution you want, but the usual ones people use are Gaussians. I'm sorry, the simplest ones people use are Gaussians. Actually, most difficult tasks these days are done with far more complicated distributions. Okay, so what did we do to try to talk about how information flows through these neural nets and compare it to renormalization? Well, we studied something called relative entropy. So I've drawn here, let me talk first about what it means or what that looks like at in the renormalization side, and then I'll talk about the neural network side afterwards. So here I have what I sort of tried to draw as a one-dimensional lattice here. I'm drawing it vertically. At every single point, there's going to be a spin degree of freedom, which is either plus or minus 1. In other words, up or down, spin up or spin down. And here is the Hamiltonian, which describes this as a simple Ising Hamiltonian. This is just a sum over all nearest neighbors. So these guys are nearest neighbors, these guys are nearest neighbors, and there's some sort of strength of interaction between them. And then if you ask what is the probability of a particular state of the system, that's going to be given by a Boltzmann distribution. Okay. I've normalized that inverse temperature, just absorbed it into all of these coupling constants. And then what we'll do is what's called real space renormalization or decimation. We'll pair up these two spins and somehow extract from them, generate from them a single spin. Similarly here, and then we do that again and again and again, okay? Each time halving the number of spins. In our case, all we do is we integrate over, or we sum over, or trace over the states of one of these spins. Let's say that one gets traced over, that one gets traced over, and that one, and then so on and so forth. Of course, that means the Hamiltonian changes as you go from left to right, and therefore the probability changes as you go from left to right, okay? So at the end of the day, then I have a probability distribution for spins here, and I have a probability of distributions after some number of steps of decimation. I would then like to compare those distributions. A very standard way of comparing two different distributions is something called the relative entropy. It's just a simple formula given here. This is the relative entropy of a probability distribution P prime relative to P, which is just given by this formula. Usually this term here is not written out explicitly, okay? Just because it's a sort of interesting case. Usually people consider cases when the two distributions are over the exact same Hilbert space and they're normalized over the exact same Hilbert space. But if they're not, then I'll have to introduce this extra term here. That's what happens here, of course. The Hilbert space halves every single time. Okay, so I have to add this extra piece. In the case of the whatever this is called, the neural network, okay, it's actually quite a bit simpler. I can fix the dimension of the Hilbert space of the neurons in every single layer by simply fixing the number of neurons in each layer. I'm not halving them at every single time. You could, but that would just make things harder. But that's it. I just feed it some input. I push through this rule. It's a fairly simple rule. It's a linear rule, except for this phi here. Phi is called the activation function, and in principle, you get to choose whatever you want to do. The simplest thing would be identity. That would be a linear network. We didn't do it with, we didn't work with linear networks. We worked with a standard activation function, which is the tanh function. There's also some amount of, let's say, black magic, if you will, here. There are some aspects of the activation function that people know that they want to have. For example, we want it to be 0 near 0. And other aspects like this, we tend to want it to be smooth, although the most common function that's used is not actually smooth. So there's the question. The point is that it's, you kind of have some choice, and in the brass tacks way of saying it is you will choose whatever works. Okay, and then theorists will then rack their brains around, why is this working? Why is this not working? But other than that, you have just this rule. And so if I have enough neurons here, and I have of order 1,000 neurons here, then I just have a bunch of neurons. They're just 1,000 numbers, 1,000 real numbers. Just plot a histogram. And so you'll have a distribution. Plot one for this guy, that's your reference layer. Plot one for whichever layer you want, and then compare them using the relative entropy. So that's all we did. Here's the results for the 1D Ising model as a function of the strength of the nearest neighbor interactions and as a function of how many decimation steps you do. So it starts off at 0 and then just rises relatively precipitously and then approaches some asymptote, which depends on the strength of your interaction. This is the exact same plot, but where we have removed the Hilbert space factor, because the Hilbert space factor is just taking into account the fact that you're halving the Hilbert space every time. I'm more interested in whatever happens besides that. I know I'm halving the Hilbert space every time. Okay? That's not really the information that I'm trying to get at. And notice, by the way, I just want to make sure it's clear that this is not the reflection of this. Yeah, the blue line here is flat, whereas the blue line here is curved. The brown line here is curved, whereas the brown line here is flat. It's more like we've morphed it down. Okay, we've sort of squeezed it down. There's an important concept here, which is when K is small, when the nearest neighbor interaction is small, you can either think of that as very weakly interacting or very high temperature. That's the same. And in that limit, all of the spins are completely decoupled from one another, right? And so if you just get rid of half of the spins, then you will get rid of half of the information. Right? You've gotten rid of half of the entire state that you started off with. What's the maximum amount of information you can possibly lose? Well, it's the entropy that was in the system to begin with, which is n log 2, where n is the number of spins, which is why actually what I've done here is I've actually divided by n log 2. And notice the blue curve, which is the low K thing, is bounded below by -1. That's not surprising. Why? Because this curve, this thing on the right-hand side is actually telling you how much information you're losing, okay, in the process of decimation. And the maximum amount of information you can lose is -1, or 100% in these units. But what's this? Why are you losing so little information when the interaction strength is strong? I think that's quite clear. When the spins are strongly interacting, then they're strongly correlated, which means if I get rid of half of the spins, let's say, that's not such a big deal. I know about their state despite the fact that they're no longer there. Why? Because the spins that I got rid of are strongly correlated with the spins that I still have. Okay. So the information about the state of the system is actually encoded in the strong correlations between the spins as opposed to individual spin product states. Okay. That's how it's able to survive decimation. So for the deep neural network, the curves look almost, well, basically the same, except of course it's a lot more random. And I've shown here curves for two different types of tasks, something called MNIST and something called CFAR10, but they're both image recognition tasks. MNIST, for example, is handwritten digits, and you have to tell me if it's a 0, 1, 2, or 3. And CFAR10 is more complicated. They're colored images, and they're images of objects like houses and boats and things like this. And you can see it's much harder to do this task than this task. The dashed curve is pre-training, the solid curve is after training. It doesn't make that much of a difference for MNIST, but it makes a huge difference for CFAR10. Just for relatedness, CFAR10 is usually done using convolutional neural nets, and I'm only using a super simple feed-forward neural net here. Okay. Now, I get roughly the exact same, the same kind of shape of curve here. However, we reached some puzzles in this case that we didn't for the 1D Ising model. So I don't know how to interpret the asymptotic value in terms of something like the initial entropy in my reference layer. We can compute that object. After all, I just have a distribution of the neurons in the initial layer, and this doesn't coincide with it. So I don't quite know. At the moment, the puzzle is how do we do something like what we did from the left to the right image for the 1D Ising model that allowed us to interpret the right-hand figure in terms of information loss. I'd like to do something like that for the neural net, but I don't quite know how to do that without, kind of pretty obviously imposing my own bias. And then some other curious fact is that actually these neural networks have a phase transition between an ordered phase and a chaotic phase, right around between this blue and the orange line. But nothing weird happens between the blue and the orange line. There doesn't seem to be any sort of divergence. And actually we repeated, after we did this, we also repeated the same renormalization thing for the 2D Ising model. The 1D Ising model doesn't have a finite critical temperature, but the 2D one does. Okay. And we found the same result, that there wasn't anything that was happening near the phase transition. So for better or for worse, this particular observable, the relative entropy, is insensitive to the phase structure. Okay. Which, okay, if you're interested in the phase structure, that's a problem. Okay. So, here's my conclusion and outlook. I'll skip most of these parts. Actually, this part should say that the asymptote value is not clear for the neural nets. They were perfectly clear for the Ising model. Okay. But we have these puzzles of A, I don't know what to make with the asymptotic value for the neural nets, and B, why doesn't it seem to be sensitive to the phase structure? Perhaps that's just the case and we have to live with it. But then I would like to find an observable, an information theoretic observable that is sensitive to the phase structure. Interestingly, there is one called mutual information that's already been done for the Ising case in this thesis by Fowler. Actually, interestingly, Fowler says that he's computing the relative entropy, but it took us a little bit of time to figure out, no, he's actually computing mutual information. But interestingly, it is sensitive to the phase structure. However, the reason why we didn't compute that in the first place is actually that vanishes trivially for these feed-forward neural networks. And the reason for that is that the neurons in a single layer aren't connected to each other. So that's why we didn't compute that in the first place. But there are a gajillion different types of objects you could try to compute. Information bottleneck, or I mean, all sorts of things that I probably don't know all of them. So you could try to do that. But I think something that's more interesting would be to do the exact same thing, but for a much broader class of supervised learning tasks. We only did, and actually I should say, not only for supervised learning tasks, but also for architectures. So we only did it for this very, very simple case. We'd like to do it for convolutional neural nets, residual neural nets, all sorts of other things. Neural nets with, skip connections. I mean, there's, the world is your oyster, basically. And, we'd like to do that in order to kind of disentangle information flow through a neural network that comes from training, as opposed to that comes, intrinsically through its structure. Before I end, I'd like to flash the paper where this talk is based off of, and my collaborators on this work, which were Johanna Erdminger in Würzburg and Ro Jefferson at Ardita. And to just say that Ro is going to move later this year to Utrecht. So they'll be actually Ro came from Amsterdam beforehand, so just returning to the motherland. Thank you very much. Not that much time for questions, but if there is a question, try Seth. Maybe speak up loud.
Yeah, Well, I guess you said you don't want to put it in explicitly, but normally my impression is that when you compare things like multi-scale renormalization ansatz to neural networks, that's equivalent to convolutional networks with pooling, where you're explicitly throwing away information at each level.
Yeah.
So I would imagine you get closer results if you look at convolutional neural networks with pooling than if you compare it to.
That's right. Yeah. No.
Repeat the question.
So the question is, or the statement I would say, which is I agree with, which is that we think that we should actually get better or closer analogy with, or closer to what happens in renormalization if you do this for the same sort of task, but for convolutional neural nets with cooling. The reason is that there is a strong mapping between this and a well-known type of neural net, or a well-known type of network called the multi-level, MIRA, multi-scale entanglement renormalization ansatz. Yeah, absolutely. It's true, and there's nothing stopping us in principle. It was mostly, that we programmed this work ourselves. We didn't use like a pre-made anything or other, and we only have a finite amount of computation. Now that I'm in Leiden, actually, Leiden has the Maris cluster, and there's also the Alice cluster. So we're hoping that actually we can scale these calculations relatively soon.
Okay, Kevin, thanks again.
Thank you.